And today our speaker is Rafael Chaves from Natal. So let me, as usual, introduce a little bit his career path. So he did the bachelor and master and the PhD all in Rio de Janeiro. And he got a PhD in 2010 in Universidade Federal do Rio de Janeiro. After that, he moved for a postdoctoral career. He stayed 2 years in Barcelona in the Institute of Photonic Science. And then he moved to Germany, where he stayed for 3 years in Fribourg, and then just 1 year in Cologne, because then he joined Natal as a professor, and now he's a professor over there in the same place. He's, as we know, an expert in quantum informations and the foundations of quantum mechanics. And today he's going to probably bridge a little bit foundations with technological applications that are coming out. And the title of the talk is Beyond Thought Experiments, Turning Quantum Foundations into Quantum Technology. Rafael, the floor is yours.
Thank you, Dario. Well, let me start thanking also Marcelo and Barbara. I don't know if Barbara is here somewhere. Well, there. Thank you, Barbara. I think the last 2 years, it's my 4th time here. So it's always a pleasure. Please keep inviting me. I would like to come more. Yeah, so as you may know, today we are having this one-day event about quantum technologies, and the topic of today is quantum communication. We've heard a lot about the different initiatives on quantum networks in Rio, Recife, São Paulo, Salvador. So the idea here is to be a bit more basic. I'm not going to get very technical. You can interrupt at any time. Please make questions. You don't need to wait until the end. It's fine. And I will try to talk a little bit about the basic concepts, basic protocols, how this can be turned into useful quantum technology. And towards the end of the talk, I will talk about some recent results of our group, okay? So yeah, here is Natal. You introduced I think the IIP is very close in mission and goals to the ICTP-SAIFR. I would consider ourselves like sister, brother institutions. We have the same goals, like to be a hub and have a lot of events and join people. So apart from our nice building, we also have some nice landscapes. Here is our group there. This photo, it's a bit old, but it was the only one I had. So we have the quantum information part that I'm taking care of, and there is also the quantum matter side of things that Professor Rodrigo Pereira is the leader. Here are just some of the events we have organized in the last years. Okay, so if you are all most welcome to come to Natal and stay there with us. Let me only put the clock here, that I don't pass the time. Okay, so let me start motivating a bit what I'm going to spend here the next 40, 50 minutes talking about. For those that were in the morning here, I'm sorry, it's going to be a bit of repetition, but for those that were not, I think it's fine. So let me just make a short story of the last 10 years, what happened in quantum networks and quantum communication. So in 2012, we had this amazing experiment by the group of Zeilinger, who won the Nobel Prize in 2022, where they managed to, in free space, share entangled photons across 2 islands in the Atlantic. Right, so over 100 kilometers, and they used these entangled photons to perform a quantum teleportation protocol. If you don't know what this is, we are going to talk more about that soon. Some years later, 2016, the distance was a bit smaller, only 6 kilometers, but the nice thing here was to show that you could use already ready infrastructure, like for telecom, and use this infrastructure to also do quantum communication. So this here, if I'm not mistaken, was in Canada, in Calgary, I think. Then 1 year more, and then it was like the real breakthrough. It was the quantum satellite of China, MISSIUS, that has onboard source of entangled states, and using that, so they managed to break all the records on distances, because the photons are traveling most of the time in the outer space, so they don't have much attenuation. the coherence, and so on. And with that, the first experiment, they distributed entanglement in 2 points on Earth that were like over 1,000 kilometers apart, and they proved that this state was entangled by violating a Bell inequality. It's something that we are going to discuss in more details here. So 2018, they had this quantum Skype call. Like this year, they did something similar between China and South Africa. Then 2021, this result appeared here today already, the quantum network of China, that it's really amazing because they, it's a medium scale network, over 100 nodes and connecting points that are over 4,000 kilometers apart. And they use hybrid technologies. They combine satellites with fibers to do quantum key distribution and many other applications. Okay, so what I want to convince you is that it's not sci-fi anymore, it's reality, it's happening. Okay, so where we are going toward, it's the quantum, so-called quantum internet. It's just a fancy name for something simple. So what's the internet? It's just a bunch of nodes interconnected by links. In the usual internet, these links are classical, meaning that we can send classical information over them, like bits that are 0 or 1. So the quantum version of it, it's the same thing. You have nodes, but now the links that interconnect these nodes are quantum channels, meaning that we can use them to send superpositions, entanglement, to send quantum information. And the nodes themselves could be like classical devices or quantum devices. Could be quantum computers, could be measurement apparatus, or could even be like a usual laptop. Okay, but why we want the quantum internet? There are a few reasons. So here I'm going to be very basic, but if you have any more technical question, I'm also very happy to take them. So there are a few reasons to want to construct such quantum networks, and the first of them is quantum teleportation, that it's over 30 years old now. And the idea here is how can you send quantum information over a network. So let's say you have quantum information encoded in an ion, trapped in an ion trap. So how you send this information from a lab here to a lab, I don't know, in São Carlos. One way of doing it would be to pack the whole lab, put in the Correios, and send this over a truck. It's a possible way of sending this quantum information. It's not the most useful one. The thing to realize here is that what we want to transfer is the information encoded in the quantum system and not the quantum system itself. So this is where quantum teleportation enters, because now what I do is that I have an entangled pair between Alice and Bob, the sender and the receiver, and there is some input state that Alice has. She doesn't know what is this input state, could be the result of a quantum experiment, and she wants to send this to Bob. But she doesn't want to send the physical system, only the information. So what she does, she interacts. So let's see, she interacts her qubit with her share of the entangled pair, and after this interaction, she makes a measurement, so she collapses the wave function. She's going to measure two qubits, so she's going to turn this into classical information, bits 00, 01, 10, or 11. She sends this information to Bob via a telephone line, and Bob here, acting on his part of the entangled state and having this classical information, he's able to reconstruct not the original quantum system, but the original information that was encoded in this quantum system. And why this is useful? Well, because I have a way now of sending quantum information without having to pack a whole lab and sending via the Correios, right? So I just use entangled pairs. The other thing I can do, and this is very useful when we talk about bigger, larger, more complex networks, it's the teleportation of entanglement, also called the entanglement swapping. So let's say that I want to establish an entangled pair between São Paulo and Natal, over 2,000 kilometers of distance. Unless I have the Chinese satellite, I'm going to use either free space or fibers. And there is no chance that a photon coming from São Paulo will arrive there in Natal. So what I have to do, I put intermediate stations, like repeater nodes, and I do a sequence of teleportations. So let's say Here I have the node A, that it's entangled with this node I, and node I is entangled with the node J. So I is going to teleport the qubit that it has entangled with A to node J. So after doing that, effectively what I have, it's entanglement between A and J. And the nice thing here is that A and J, they never interacted. So I established quantum correlations between two sites that have never seen each other, that have never interacted in the past. And if I do a sequence of these things, you see, so I make São Paulo to Rio, Rio, Salvador, and so on and so forth, and then I can establish a link between São Paulo and Natal. The other kind of protocol that we can use is the super dense coding, that it's the kind of reverse of quantum teleportation. In teleportation, I use entanglement plus classical information to send quantum information. Here, I use entanglement plus quantum information to send classical information, but in a more efficient way. So it can be proven that like sending a qubit, I can actually send 2 bits of classical information. And here, something that we've also heard today, how is this? Okay, here, that it's the so-called distributed computing, that it's very useful in when we talk about cloud computing, that it's the idea that I have a mainframe, like a server, that has all the computational power I need, and the data that it's going to use to compute a given function, it's distributed in the network, in these outer links here. And classically, of course, what I have to do is that I have to send all the information that I need from these stations to the central station. But it's known that if for certain functions, for certain communication protocols, if I have an entangled state shared here among these nodes in the network, the amount of information that I have to send, it's smaller. And in some cases can be exponentially smaller. So it's like one example of exponential quantum advantage for quantum communication. The other thing I can do, that it's perhaps the most famous and perhaps also the most useful, it's quantum crypto. I'm not going to enter in the details here because we are going to talk a bit more about that later on, and we've heard a lot about that today. The other thing that also it's quite useful, it's what we call blind quantum computing, that it's the idea, well, okay, for the next decades, it's very likely that quantum computers will remain expensive, complex, and fragile. So Brazil now is going to invest, apparently, at least according to Folha de São Paulo, a lot of money in quantum tech. So in a few years, we are going to have our own quantum computers. But yeah, there are going to be very few of them. So we, as scientists, we are going to use them via a network. And here I have 2 problems. One is the security over the network. So I'm sending information, maybe sensible information over a network. This problem I can solve using quantum cryptography. We are going to talk about that later. But the other problem that it's more fundamental, it's how can I trust the server? So let's say I'm sending input data that, if it's correct, could solve the problem of energy. Like I could, I don't know, find a solution to generate energy for free. So, of course, everyone wants this data, so how can I be sure that the server is not going to steal this data? More than that, how can I be sure that the server is going to do the computation that I want it to do? And this is a problem, because I'm using the quantum computer because my normal laptop cannot solve my problem. And in many cases, how can I verify that the quantum computer is actually doing what it's supposed to do? And blind quantum computation is the answer to all of that, because using this network scenario, I can guarantee that the server is blind, doesn't know what it's computing, doesn't know what's the input data, and at the same time can verify or can certify that it's actually doing the computation that it promised to do. It sounds impossible. It's one more of the tricks of quantum mechanics. Okay, so I spent 10 minutes with my motivation, but don't worry, I will stay on time. So here's the outline of the talk. I will start talking very basically about non-classicality, or my notion of non-classicality, and how it relates to Bell's theorem, the Nobel Prize of 2022. Then we are going to have a crash course on quantum crypto and randomness, like how to apply Bell's theorem in this setting. And then in the last part of the talk, I'm going to talk about how we can witness non-classical behavior in quantum networks and how to turn these witnesses into useful tools. So these two last points there, I'm going to talk a bit more technical results or like results from our group. Okay, so non-classicality and Bell's theorem. So what I'm going to define here as non-classical, it's different from what Daniel told us earlier. He defined non-classicality by the correlation function. It's a valid measure of non-classicality. Here, for me, non-classicality will mean entanglement, okay? Or classicality will mean separability. So if I have pure state, it means that I can write it down as a tensor product of its parts, or if it's a mixed state, it means that I can prepare this state via LOCCs, like local operations and classical communication. The question then is how you give me a state, and I have to tell you if this state is non-classical or not, if it's entangled or not. How can I do that? There are different ways, and these different ways, they are related to how much I trust my devices. Okay, so let's say that I'm a very good experimentalist, Daniel, Zella, or all the other good experimentalists that we heard today, they know what they are doing. So they know that if it comes a photon with information encoded in the polarization, they know that if they put a wave plate there in a certain direction, it's going to measure the sigma x or the sigma z direction. So if I can trust my device, and I can trust that my information is actually encoded in the polarization, then I can just perform an entanglement witness, where I do here the tomography of the state, so I know what's the encoding I'm using, I know what's the measurement device I'm using, so I just do the tomography of the state and check if it can be written in this form or not. This is what we call device-dependent approach, because I trust what I'm doing. But now let's say that it's entangled state. Zella, he trusts his device, but he's not so sure about Daniel. So he said, well, yesterday we were up to until late, drinking some beers. I'm not really sure I can trust what he's doing in his lab today. So now we are not going to trust this device anymore. We are going to put a black box around it. And instead of assuming that I know what I have on this side, I'm just going to look at the, so this is not working anymore. I'm just going to look at the experimental data it generates. So I'm going to press some buttons, and this button, like after I press a button, I get an outcome A. So I press a button X and I get an outcome A. And now I can go to the full paranoid scenario where I can say, well, I actually don't trust my sources and I don't trust my measurement devices. In this case, I'm in a full black box scenario that we also call device independent. And this is related, as we are going to see, to Bell non-locality. And this is extremely connected to quantum crypto, because in quantum crypto, the less you assume, the more secure you are. So if you buy these devices from a company, you don't want to trust them. You don't want to, well, they are really selling me what they are telling me that they are selling. So
sorry,
I don't need to trust them. Yeah.
Beyond being trustable or not, there is also, let's say, a trend in, how can I say, complexity, like, because I know that, let's say, full quantum tomography is very expensive. It's very also demanding. You need many copies of the state, and they have to be all equal. Because, so do you gain something in going down on that or not?
Yes, you can. Like in some cases, so for tomography, the number of measurements that you perform, they increase exponentially. For Bell non-locality, for instance, you have a very good non-locality test that the number of measurements increase linearly with the number of systems. So yeah, you also have this advantage. Okay, so this connects to the old discussion of Bohr and Einstein. Here, like the position of Bohr, expressed by this famous phrase of Jordan, and here the answer of Einstein as a famous question, right? Like, do you really believe that the moon only exists when we look at it? So what he was questioning here was this idea that properties of a physical system, they should be defined independently of whether we measure them or not, right? So this was in 35, and then in 64 came Bell and kind of solved the paradox. And here, I'm going to give you like a kind of modern version on Bell's theorem. So what is Bell's theorem about? We impose some causal structure to our experiment, and the question is whether a classical description of this causal structure is able to reproduce the quantum predictions. And in Bell's theorem, we have a very simple causal structure where I have a source that can produce here physical systems. These physical systems are sent to Alice and Bob. Alice and Bob are very far apart. Alice, she chooses something to measure. We are in a black box scenario, so she just presses a button and get an outcome, and the same for Bob. And here is the underlying causal structure. So you see, like we have a source. So this source, we are going to assume it's described by a random variable, lambda, that I might treat as a hidden factor, because I might not have access to all the degrees of freedom of it. And of course, the source is going to affect the measurement outcomes of Alice and Bob. Depending on what I prepare, I'm going to change what I observe. And of course, that what I observe will also depend on what Alice and Bob are going to measure, okay? So here, what is behind this causal structure, it's three assumptions. The first one is what some people would call realism, that it's basically saying that such hidden factor exists and has a well-defined probability distribution. And we have two causal assumptions. The first one is the usual one, the locality assumption, that is basically telling me what Bob is going to observe in his lab should be independent of what Alice is doing in her lab, because they are very far apart, and vice versa. And one other assumption here that has nothing metaphysical about, but we call it the free will, that it's basically saying that Alice and Bob, they can choose what they will measure independently of each other and also independently of how the source has been prepared. Three very natural assumptions: free will, realism, and locality. And as shown by Bell and later by Clauser, these imply Bell inequalities. So these three assumptions, very natural assumptions, imply constraints to what I can observe in my experiment. One of these, these constraints we call Bell inequalities, and one of these inequalities, the most famous one, is the Siege-Sage inequality, basically saying that the sum here of these expectation values, if I fulfill these three assumptions, should be smaller than 2. So here it's just like the expectation value of the outcome A of Alice, the outcome B of Bob, given that X is equal to 0 and Y is equal to 0. And quantum mechanically, I can surpass this bound, achieving the maximum that it's 2 square root of 2. So this shows that whatever quantum theory is about, it should be incompatible with at least one of these three assumptions: free will, locality, and realism. You can choose. I will give you my opinion. I give up realism, but there are people that give up free will and so on and so forth. Okay, so
sorry, just to connect. This, let's say, people still work on hidden variables and so on because they don't give up realism and they give up something else, or how?
Well, for example, like if you are Toft, you give up free will. So his theory, you have no free will. He give up this. Yes, it's everything deterministic. Or if you are Bohmian, you give up locality. And I mean, we are restricting more and more. Things are getting more and more difficult for the realists, but the option is still there. Okay, so the point here is that it's this, right? We are imposing a given causal structure to my experiment, and if it's classical, I just use here basic probability theory. I'm not going to go through the steps here, but in the end, if I just use these three set of assumptions, I see that everything that is classical in the causal sense should be decomposable as something like this, that it's basically saying that, well, there is a probability distribution that describes my source, and Alice and Bob, I can describe what they observe in their labs by local response functions. So it seems very natural, but like entangled states violate this here. And one important thing is that every separable state, or every state that is classical in my assumption, is going to admit such a local hidden variable decomposition. So what this means is that if I violate the Bell inequality, I can be sure that my state is non-classical. And it's a device-independent proof of that. I don't have to trust that I'm measuring the polarization of my photons. Could be ping-pong balls, for that matter, it doesn't matter. Or I don't have to trust my device. And geometrically, so this is quite nice because everything that is classical or that admits this local hidden variable model should fall here inside what we call a local polytope. Like this gray region here is the region where I have my classical correlations. The boundaries of this set are exactly Bell inequalities. This purple region here that includes the gray one is the set of quantum correlations. So the set of quantum correlations is bigger than the classical one, of course. And I could even go wild and think about post-quantum theories, like things that are not exactly quantum. I can also naturally introduce them into this setting. Okay, so that was our introduction or definition of non-classicality. So let's see how we can use this for some application.
Sorry, can you give an example of post-quantum? Something that's not quite quantum?
Yes. So for instance, we know that quantum theory is compatible with special relativity. I cannot use quantum mechanics to send information faster than light, right? So now there is this famous paper, I think 92 or 94, by Popescu and Horlich, where they said, is quantum theory the only theory that it's compatible with special relativity? And the answer is no. There is a whole continuum of probabilistic theories that respect special relativity in the sense that you have to respect that signals have a maximum speed limit and still go beyond quantum theory. And how they prove that? It's using Bell inequalities. So basically, but if you impose only special relativity here, what we call non-signaling, you can see that this Bell inequality here can be violated up to 4, while the maximum quantum violation is 2 square root of 2. So there is a gap of probabilistic theories that go beyond the quantum theory.
Can you just tell, what's a small parameter you introduce into quantum mechanics which allows you to deform away from quantum mechanics?
You don't have to talk, so this is the beauty and also the problem of this, this approach. You don't need to talk about the theory itself. You only talk about the correlations it generates because you are in this device-independent setting. But this is quite powerful. Like I'm going to mention a result later on that allows to tackle this sort of questions.
Related to that, sorry. One of the beauty of quantum mechanics is that, let's say, probability is not the fundamental object. The fundamental object is the amplitude, and only the square is a probability. And that is beautiful because, let's say, quantum advantages of this post-quantum preserve the structure that, let's say, probability is only a derived quantity.
You can, so you have the so-called GPTs, like generalized probabilistic theories, where you extend the notion of state and of measurements. And then you can talk about these sort of things, yes. Okay, so quantum crypto and randomness. Here, like crypto 101, I'm sure you have heard of that, but like Caesar's cipher. It's a way of like encoding information. So let's say you take the alphabet, A, B, C, D, and so on, and you just shift it by a factor of 3. So A becomes D, B becomes E, C becomes F, and so on and so forth. So let's say that the message, that the original message is something like this. If I just apply this shift, I see that the ciphered text, it's going to look like something horrible like this. So it looks that, well, it's encoded, but actually it's very easy to break this guy here. Like you can just test all possible shifts that you could use, or you can use even like statistical analysis, and you say, well, okay, if I know that this message is in English, it's very likely that the letter that it will appear most, it's the letter E. So I just look here at this ciphered text. What's the letter that it's appearing more often? It's age. So I will say, well, most likely age, it's going to be equal to E, and then you just decoded the ciphered message. So just say that there are ways to encrypt messages, but there is always someone smarter than you to decrypt it. So what can we do? And this is the only way how we can cryptograph messages, and this is proven to be secure. It's the so-called one-time pad that is related to secret keys. So the idea now is that Alice, the sender, has a secret key, a sequence of zeros and ones that only she and the receiver, Bob, have access to. So basically, what Alice is going to do, she has like some message MI that she wants to send to Bob, and she's going to encode this into a message C, where she's going to basically make the sum modulo 2, like bitwise, of her message with the secret key. Okay, so she sends this C to Bob, and Bob on the other side has access to C, and if he has access to the secret key, he just makes the sum modulo 2 again, and he's able to recover the message. So the nice thing here, it's this, right? That Bob can't recover the message, but there is an assumption that Alice and Bob, that this secret key that they have, that it's actually secret. So it means that like Alice and Bob had to meet somewhere in the past, and then they had these secret keys, and they are using them. Of course, we can, like, this is not very practical. And there is one problem also, and it's where this one-time pad enters, is that if they keep using the same secret key, you are able to review what is this secret key. So here, for instance, let's say that Alice had two messages that she wanted to send to Bob, message M and message N, and she encoded these into a code 1 and a code 2. If the eavesdropper, if the hacker that it's listening to this communication just make the sum modulo 2 of these two guys, he gets information about the sum modulo 2 of the two messages that Alice wanted to send. And if the eavesdropper keeps doing that, and Alice and Bob keep using the same secret key, then then this scheme is not secure anymore. So to be secure, Alice and Bob, they need to have secret keys, and they need to use them only once. So these are the conditions to achieve cryptography. The question then is, how can I establish the secret keys between these two distant parties? And classically, I cannot do that, but quantum mechanically, I can. There are many variations of this here. I'm going to use the standard form that we use when we connect this to Bell's non-locality and to Bell's theorem. Okay, so I have Alice and Bob. It's the same scenario I had before. I have here an entangled state or something else that I don't know. I'm just pressing buttons and getting outcomes. But now I say, well, I'm not sure that we are alone. I might have some eavesdropper in between. And what's the most general thing that an eavesdropper can do? Actually, the eavesdropper sells you a device that prepares quantum states, but these quantum states are not anymore bipartite states. Could be tripartite states. So she's trying to steal part of the information of your system. So if we just use Born's rule, this is going to tell us that this system is going to be described by a probability distribution of Alice's output, Bob output, and now also Eve's output. And by Born's rules, this is just going to be the trace over some measurement operators here for Alice, Bob, and Eve over some tripartite quantum state that potentially was prepared by Eve. She has control over it. Okay, so we are in a very bad situation. How can I be sure that she's not stealing all the information? I have to use now properties of quantum mechanics, and the first one is what we call self-testing. it's possible to show that if you take this CH-SH inequality and you violate it up to its maximum of 2 square root of 2, there is only one way that you can achieve that, is if the state shared between Alice and Bob is a maximally entangled state. This is the only way you can achieve 2 square root of 2 in the CH-SH inequality. And then, if I can guarantee that I have a maximally entangled state between Alice and Bob, I use a second very basic result in entanglement theory called monogamy of entanglement that tells me the following. If the state of Alice and Bob is a maximally entangled state, then I have the guarantee that this state, this maximally entangled state, is uncorrelated from the rest of the universe. So because of this, we call it the monogamy. I'm so attached to someone that I'm blind to everything else, okay? And okay, if now I can guarantee that whatever Eve has prepared must be uncorrelated from the state of Alice and Bob, it follows then that their probability distribution should factorize. So whatever Alice and Bob are generating here should be independent of what Eve is going to achieve here. And this means that the best guess that she can do about the outcomes of Alice and Bob is a random guess. The best thing she can do is to flip a coin, okay? So this is very nice because it shows us how to use the structure of quantum mechanics to guarantee that even if there is an eavesdropper, she's unable to achieve any information about my secret key. But of course, I will never achieve maximum quantum violation of a Bell inequality. I always have some sort of noise, decoherence, and so on. But I can move beyond that. So here, I think it's among the first papers that showed that by Pironio and some others in Nature 2010, where they showed the following. So here, this red curve tells you how much randomness you have as a function of the of how much you violate the CH-SH inequality. And actually, you can prove that if you violated the maximally 2 square root of 2, then you can extract 1.23 bits of randomness, of certified randomness. I can guarantee that Eve doesn't know what are these bits. But then, if I violate less, because I have noise and so on, then, well, I'm going to violate less, but I still can guarantee a bit of randomness. So this curve here, it's certified randomness. I know that these bits are unknown to the eavesdropper. And here, this blue curve, it's how much randomness I can generate if I play against these post-quantum theories. So even post-quantum theories allow for some randomness. Okay, good, let me see. I'm good on time. Let's talk about some more recent applications of that. So first, witnessing non-classicality in quantum networks. So here is the network that we've been speaking so far, Alice and Bob, or here I'm calling Alice1 and Alice2. You see, it's a very boring network. I have a source, I have here an outcome here, and inputs. Over the years, many people tried to generalize that, and there are nice generalizations. And one that I would call it's a bit boring, that we have the multipartite Bell scenario. You still have a single source, but now it connects not only 2 observers, it can connect 3, 4, 5, n observers. This has a lot of useful applications in quantum communication, but this, I would say, is the first step. Why not to move beyond that? And surprisingly, the first ones to do so, it was the group of Gizan in 2010, where they said, well, if instead of having this network here, I have something like this. Instead of having like a tripartite state that connects Alice1, 2, and 3, I have now a true network. So I have an entangled source between nodes 1 and 3, and I have another source between nodes 2 and 3. And now this node here in the center, it has 2 qubits. So if it has 2 qubits, it can make measurements on an entangled basis. So this sort of networks here, they naturally introduce something that I don't have in this network. That it's the possibility of not only having entangled states, but also doing entangled measurements. And the other thing that it introduces, it's a lot of mathematical complexity, and it's going to be clear why in a second. Okay, so let me just tell what sort of things we can do with this it's a network, but still a very simple network. And over the years, like we and other people discovered a lot of nice results. One, it's the so-called non-locality activation, that it's the idea that you put here a state that if you just test a CHSH test between nodes A1 and A3, or between A2 and A3, all the correlations you generate, they are always going to be classical. So even though the state might be entangled, you never can certify that. But now, if you put them into a network, and this central node here can now make entangled measurements, you can review, you can activate the non-classicality of these states. A more recent result that I don't fully understand, but I find very cool, that it's self-testing of quantum theory. It's the idea that simply looking at the data, like you press buttons and you get outcomes, you can test whether quantum theory is the theory or not. So, I mean, this is what I have to say here. Like, in principle, this could have applications to quantum gravity and these sort of things, because if you are in a device-independent setting, you don't need to know exactly what the theory is. You basically make measurements, and these measurements by itself, they might reveal something about the theory. One result, also very cool, it's this result from 2021, where they used this sort of network scenario to prove that nature needs complex numbers. And what I mean with that, you can ask, well, complex numbers could be just some mathematical artifact, like a more efficient way of representing math. But according to this result here, not, because they test a Bell inequality in this scenario, and what they show is that the only way to explain experiment, like what they observe experimentally, is if indeed complex numbers are part of nature.
Sorry, so self-testing quantum theory. So again, is there some deformation of quantum theory? I mean, it's obviously life is approximately quantum, right? How do you prove that it's not exactly quantum?
Yes, because you are looking to the correlations that quantum theory can generate. So you look to this sort of figure here. Let me find it. This. So if you assume quantum theory, you are going to see that all the correlations that can be generated by the structure of quantum mechanics are going to define a convex set of this form here. And now the idea is, well, if I go to the experiment and I find something that it's outside, I just disproved quantum mechanics. And I even don't need to know what this theory is. So this is the easiest way of looking at that, but there are more intricate ways here. But the point is this, it's like, okay, I know that that quantum theory should be bounded by this purple region. If I find something out, I disprove it quantum mechanics. And I don't think this is going to happen, at least not in tabletop experiments, but yeah, like it's a way of testing the correctness of quantum mechanics, even without knowing what could be the post-quantum theory. Okay, so, well, there are other applications here. Let me talk about the mathematical difficulties here, because this is where I spent 5 years of my life. So, yeah, like these networks, they introduce a very complex problem, because now the fact that you assume that some of the sources in your network, they are independent. So remember, in the usual Bell scenario, you have a single source, right? Here you have many independent sources, and these independent sources, they introduce nonlinear constraints. So now, instead of describing a polytope, that it's a convex set, you are describing a high-dimensional non-convex set. So here it's like a two-dimensional cut of how these sets might look like. So these petals here of this flower are like non-linear Bell inequalities, and the idea is that if you find a point outside the set, then you can be sure that the correlations you are generating are non-classical, okay? So many people have looked at this problem, like there are full general solutions that are rooted in algebraic geometry. I don't know about you, I'm not smart enough to understand what this is about. So over the years, me and other people have tried to develop new tools to tackle this sort of problems. And what's the problem again? It's how to describe the set of correlations that a given network might give rise. And over the years, we developed the numerical tools and also analytical tools. I'm not going to dive into the details of these things, but just to give you a glimpse of how complex these things are, if I take here a very simple network, that it's this network here, I have Alice, Bob, and Charlie. Alice and Bob, they share an entangled state. Alice and Bob share another entangled state, and Bob and Charlie share another entangled state. This is what we call the triangle inequality. And then you can run these codes, and one of the Bell inequalities that you get, it's this thing here. Compare this to this CHSH inequality, right? So just say that the problem is horrible, but we have the tools now, and we can use them for nice things. And it's what I'm going to talk in the last 8 minutes, I guess. Okay. So here it's an experiment where we, with Fabio Chiarino group in Rome, where they did, I would say we, but I didn't do anything, just the theory, where we do a quantum network involving 3 nodes. So I have Alice, Bob, and Charlie. Here's the network. I have Alice, Bob, that it's the central node, and Charlie. And the nice thing here is it's 2 things. So the first is that it's a hybrid network. One of the sources, it's a quantum dot source. The other source, it's a SPD source. One of the links, it's a fiber link, and the other link, it's a free space link. So we wanted to like simulate a like a real network, but that has different technologies. And then what we did here was to test whether these correlations that we generated here in this network, they were non-classical or not. And there are 2 ways of doing that. One way is to assume the usual Bell's theorem, where I have a single source. So now I say, well, I don't know the structure of my experiment, so I'm just going to assume that I have a single source interconnecting these 3 labs. And then what I see is that the experimental data that we generated here, this is a star, would fall inside the local set. So this data that we generate in the experiment would be classical. But now the question is, and if I assume that the 2 sources are indeed independent, instead of saying that I have a single source, I have 2 sources, then I have a new Bell inequality, that it's this so-called bilocal inequality, and the data that we generated here, it's outside the set. So we are showing that by using the independence of the sources and using these ugly inequalities, we can certify the non-classicality of the data, something that would be impossible otherwise. This was like a 3-node network, and then they said, well, why not to try to increase? Then we did this next experiment that now we had 5 nodes and 4 entangled states here. So this was a nightmare to synchronize, or at least this is what the experimentalists tell me. But the nice thing, it's here. Look, the experimental point, it's here. You see, it's very deep in the classical set, but it's outside the classical set when I assume that the sources here are independent. So if I would not assume here that the sources are independent and use these ugly inequalities, there is no way I could certify that this point here it's non-classical. Another experiment, also with the group from Rome, and here it's really a beautiful result for a number of reasons, but I will focus in one. So here is the structure that we have. We have a state between Alice and Bob. We have another state between Alice and Charlie, another state between Bob and Charlie. And notice here that I do not have inputs. Alice, Bob, and Charlie are always measuring the same thing. In the usual Bell scenario, if Alice and Bob always measure the same thing, I never can reveal the non-classicality of the state. It's easy to reproduce the statistics if I always measure the same thing. Not in quantum networks. So here, in a certain, I mean, the title is a bit, well, it's correct, but it's, many people don't like. Basically, what we claim here is that we are doing a Bell experiment where actually you don't need to assume free will. That it's something that you have to assume in a standard Bell scenario, okay? Okay, so this is like the how to use quantum networks and these ugly looking Bell inequalities to reveal non-classical behavior where it would be impossible otherwise. So let me finish now with some applications of that. So here it's a work that we did with the group of Alessandro Fedrizzi in UK. So here we have a single source of entanglement. I have a tripartite network, but here I have a single source, so it's a convex polytope, it's everything fine. But it's a structure where I don't have the locality assumption anymore. It's a structure where LS1, she can send information to LS2, LS2 can send information to LS3, and LS3 can send information to LS1. So you can understand like a cycle, right? This is represented here. Here's the lab of Alice. She's sending information to Bob. Bob is sending information to Charlie, and Charlie is sending information to Alice. So it's a Bell scenario where we are relaxing the locality assumption, and what we prove here in this experimental paper is this communication complexity gap. So we show that if they have here a JZ state shared between these three nodes, they can compute functions in a central node in a way that they have to send less information that they would have to send if they would not share entanglement. Okay, so it's a practical application of this network. Here it's related to randomness, and it's a nice scenario. It's a scenario that won the Nobel Prize in Economics in 2021. So I like to say that this is the interface between Nobel Prize of Economics 2021 and Nobel Prize in Physics in 2022. This is the so-called instrumental scenario that it's very used when you do causal inference, like in economics, you want to know if a vaccine is really helping against a disease or a drug and so on and so forth. Like the experiment that you are going to do, it will have a causal structure of this kind here. I'm not going to enter into many details. And then what we did in this paper was to say, well, you see here what's going on. It's like Alice and Bob, with the difference now that Alice and Bob do not have the locality assumption anymore, because now Alice is explicitly sending information to Bob. So I'm giving up the locality assumption, and in another paper we proved that you can prove a stronger kind of non-classical behavior, and in this paper here we used that to certify randomness, giving up these locality assumptions. So the nice thing here is that you can certify randomness even if you don't have space-like separation. You can be in the same lab, and you can do that in a device-independent way. So I will finish with two recent experiments that are in the archive. I will mention very briefly what they are about. So here it's with the group of Sergey and Geoff Pride in Australia. And the idea here was to use a quantum network to improve the amount of randomness that we can certify in a given quantum experiment. So here, it's like the usual Bell scenario, Alice and Bob. And what we did in this experiment was to consider what we call the broadcasting network. So Bob, he's receiving a physical system, like part of this entangled state, but instead of just measuring it, he's going to apply a broadcasting channel. So basically, he's going to try to make the best copy that he can, and he's going to distribute this best copy that by the no-cloning theorem cannot be a perfect copy. He's going to distribute this to Bob 1 and Bob 2. So now I constructed a tripartite network with inner structure based on an initial bipartite one. And what we could prove, like theoretically and experimentally, is that the amount of randomness that you get when you do this kind of broadcasting, it's this green curve here, that it's significantly higher of what you would get, that it's this yellow curve here, if you would just test the CHS-H inequality. So the message here is that networks allow you to increase the amount of randomness that you can generate in a quantum experiment, that you can generate and that you can certify. Final example, this was with the group of Fabio. Again, this is something that we wanted to do for a long time, and we managed to do early this year. Okay, so here it's again the standard Bell's scenario. Here it's a network. I have two independent sources. I have Bob here in the middle making an entangled measurement. And now you see that in this network scenario, I have a lot of possible eavesdropper attacks. I could say, well, I could have two independent eavesdroppers, E and F, where each of them have access to a single source of my experiment. I could have a single eavesdropper that accesses these two sources independently, or I could have a single eavesdropper, like the super eavesdropper, that like can process these two states and then generate an output. And then using these tools that we developed over the years, we managed to certify how much randomness you can generate in these scenarios. And here comes the first surprise. If Alice and Charlie would just make a Bell test between them, the most of randomness that they could extract would be 1.23 bits of randomness. But in this scenario, where you assume these two independent sources, you can extract up to 1.41. So again, by using the network structure, you can generate more randomness that you would in a standard Bell scenario. And here, they didn't have to redo the experiment. We had an experiment that was done in 2017. And basically what they did was to take our new theoretical framework and take the data that they generated like many years ago, and they could prove for the first time in a quantum network that they actually generated bits of randomness. So this is illustrated here and here in this plot. Okay, so I come to the end, and I think the message here, it's in both directions. So quantum networks are very cool. They're very hard to describe, but we have done the dirty work in the last years. So now we have a bunch of numerical and analytical tools to analyze such networks. And with these tools, like a lot of foundational and application results are emerging. So I mentioned some of them, like that quantum networks, they can review new properties in the foundations of quantum mechanics, this need of complex numbers and other ideas. Well, new methods are needed, but we kind of have them. And new forms of non-classicality can already be tested experimentally, and more than that, they lead to improved protocols in randomness generation and certification. So they are not only a cool foundational concept, they also have applications for the main topic of this day today, that it's quantum communication and quantum networks. So I thank you for your attention.
Thanks a lot, Rafael. Times for questions. Okay, so do you? And yeah.
So you mentioned the synchronization of the network. All the experiments need the synchronization of the sources, or just a subset of it?
I would say that at least in the current form, they need, yes, because if you don't synchronize, like it's this, you might be, if the window is too big, like you might be measuring photons that are not entangled, and then they're going to reduce the violation and these sort of things. So there are ways of like avoiding this synchronization, but like at least experimentally, we have never tried something like that. So yes, as far as we know, you need this synchronization. So you have to synchronize, like in this experiment here, we had to synchronize 8 photons. So it was complicated, yes.
More questions? Okay, perhaps I have perhaps I have a very basic question. And when you explain about monogamy of entanglement,
Yeah.
Can you go again to the slide, because I'm not sure I remember.
Here.
Exactly. So you say that by self-testing, they can decide if they are screwed or not. But by self-testing, they also destroy the state. And so is this a kind of measurement that somehow makes useless the entire...
Yeah. So like here, it's everything statistical, right? So you have to prepare a lot of states, and you have to measure them a number of times. And then some of the states you are going to use to make the parameter estimation. So you are going to burn many of these states to see how much you violate the CHSH inequality. And if you violate high enough, then you can be sure that on the other rounds, Eve is going to be independent of Alice and Bob.
Okay, so you have to assume that Eve either enter at the beginning or never enter anymore.
No, you assume that Eve doesn't know when you are going to make these tests or not, right?
Thanks for the nice review, Rafael. So I've been, over the last 2 years, I would say, invited several times for Marcelo's Terra Cunha's thesis, and they're all into contextuality and things that Barbara likes a lot, that I didn't even know existed before participating into his committees of his students. And my question is, all of this discussion you put forth builds up on entanglement in a way, right? It's directly connected to the structure of Bell states and etc. So I like to think of entanglement as something that builds up on the resource of or you can use it as a resource and explore non-locality in a way, right? So when you add, I know you are also into that. I was in a talk by Robert Speckens on the conference March meeting this last March, and he's all about this causal structure that you are discussing here, and I'm completely naive on that, but my question is, if you bring in contextuality into this, what do you foresee as potential for exploring experiments in this area? Because this is something I have a hard time with Marcelo Terra Cunha, which is he's so deep into the fundamentals that he doesn't really care about trying to picture an experiment where you can untap, let's say, the resources of contextuality. So have you been discussing this with your experimental partners, or do you have ideas that we could build in Brazil to explore this and perhaps find new answers to this?
Yeah, so I'm going to give you my view, but certainly Barbara is the expert on the topic, so she can complement anything I say and say much more. Yeah, so it's fair to say that Bell non-locality, like the standard Bell scenario, is a particular case of a contextuality scenario, right? Because in contextuality, like, you have to assume that some of the observables that are measured are compatible and some are not. So in a Bell case, like, what makes this compatibility between observables, it's the space-like separation of them, right? So they are like in different Hilbert spaces, so they are effectively compatible. So a standard Bell scenario certainly is a particular case of a non-contextuality scenario. But then Barbara can disagree with me. I think that Bell is more fundamental because, like, to assume compatibility using space-like separation, it's something that I think most of us can agree on. But, like, how can you really assume or certify that two observables in the same lab are going to be compatible or non-compatible? You just can't, as far as I know, right? And the other thing is that when you move to these quantum networks, for me, it seems kind of clear that non-locality or Bell, or this generalization of Bell's theorem, it's no longer a particular case of contextuality. I'm not 100% of that, sure of that, but it's what I would claim without proof. Yeah, but this doesn't mean that contextuality, like there are few experiments where people violate contextuality inequalities and they use that to certify randomness. So I would say that for applications, contextuality needs to assume more, while Bell has, or generalizations of it have to assume less. But at the same time, if you assume more, you get nice features as well, right? So, but your question is what could be done experimentally, right? So, well, I think Barbara can answer that better than me.
Well, first, I totally agree with you. So in order to apply contextuality, you need more assumptions that in the case of Bell scenarios are guaranteed by spatial separability. And in other cases, you just have to assume that. And in some situations, the physics of your system allows you to make those assumptions, and in others, not so much. So from the foundation's point of view, some people say that contextuality experiments mean nothing because you can never be totally sure that those assumptions can be, that they are correct to rule out, for example, hidden variable models and this kind of thing. What we have today, and it's one of the main topics that we work in our group, is to try to change the framework in order to make those assumptions more clear. So you know which assumptions you are making and if your system obeys that or not. On the practical point of view, we don't care much about that because we are not trying to prove anything or rule out anything. We're just trying to make something more efficient than you have on the classical side. And there are many things that you can do with contextuality. So contextuality appears in quantum computation, for example, and random number generation. So you have the advantage that you don't need entanglement to do that. So in some sense, it may be more simple, but you have to assume more, but you have more situations in which you don't need that much effort, for example, to generate entanglement and other things. And we have contextuality in other things. For example, we're now investigating experiments in quantum gravity and thermodynamics, so we see contextuality as giving you more power in quantum engines, for example, and this kind of thing. And the advantage is that you have many situations in which you have a protocol that does not have spatial separability. And then it doesn't make sense to talk about Bell tests. So that would be the advantage. But you have to be more careful on the assumptions you are making. So some experiments in contextuality, they were not that careful, and that's why there was a lot of criticism, and that criticism, it is correct.
Yeah.
Hi. Actually, so first of all, thanks for the great talk. I just want to join the discussion, actually, because Gustavo's question is actually great because Terra Cunha and Rafael Rabelo, they have a paper on a joint Bell inequality and contextuality test, right? And it was performed experimentally by a Chinese group. And actually, Luis was my student and is now Gustavo's student. During his master's, we tried to find a way to use those programmable chips. I mean, could you implement that test on a chip? And the answer is yes. And it actually, the issue of contextuality interests me in a way in view of those programmable chips, because you need compatible observables. And with these programmable chips, the question then becomes, how compatible can I make my observables experimentally? Because on paper they can be perfectly compatible. So I'm actually interested in knowing if we could use compatibility or contextuality tests to check the quality of the operations we can implement without having to do full tomography.
Yeah, so I mean, if I understood correctly, like it's kind of the reverse, and yes, you can. Like in a sense, like if you violate, so let's say just to connect with Bell, you can say if I violate Bell inequality by that amount, I can ask how much I have to relax the locality assumption, right? If I relax totally, then I can explain everything. But let's say that I violate 2.5, the CHSH inequality. Then you see that the amount of communication that you need to have between Alice and Bob, it's, I don't know, like 0.3 bits of information. And you can do the same thing in contextuality. If someone did or not, I'm not sure. But you can use the violation of a non-contextuality inequality as a way to measure how much your system had to deviate from compatibility. You know, so like you can use the violation. It's not exactly what you want, but you can use the violation to say, well, I can guarantee that my measurements are at least this incompatible.
Okay, yeah, that's nice to know. Yeah, it's interesting.
Okay, more questions? I remind that there will be also the round table, so I would like to keep, let's say, the questions here and the discussion later, but yeah.
So I know that you have some of the experiments in the network involves more than one SPDC source. So how can you distinguish from multiple emissions from a single source? I mean, 2 photon pairs from a single source, from having 2 pairs in one in each source. No?
I think you can't.
Because they have the same order. They are in the same order of magnitude, no? The probability.
Yeah. I mean, I'm not sure how to do it, but I'm sure that we didn't do that here. So it could be that you have higher order terms happening, but I'm not sure that these spoil the. As long as the sources are independent, I think it's fine, because it's device independent. So as long as you can guarantee that the sources are really independent, they are not acting in a correlated manner, I think it's fine.
Okay.
Okay, so we can probably end up here the colloquium, and I invite everybody for the round table after the tea time.